Hello and welcome to ATAR Notes. We are a business that concentrates primarily on resources for high school students doing the ATAR system. So we're really concentrating on getting you a good ATAR at the end of your experience during high school. We do things such as study notes, lectures like the one that I'm recording right now, videos, newsletters, and I think our most popular item is probably ATAR calculator, where students can anxiously, predict where they might be at the end of the year. So today, this is a pre-recording, by the way. We're looking at Specialist Maths Unit 3. Some of the content in Specialist Maths Unit 3, mainly, like, I would say 2/3 of the more basic ideas in Specialist Math Unit 3. We're not going to look at really hard problem solving questions, but the more basic stuff that you can use then to sort of springboard yourself into the more complex questions. So we're going to look at specifically proof by induction. Now that is sums and divisibility. So for sums, we're going to look at basically how do we do proofs to show that a sum can be modeled with a general formula. With divisibility, we're going to prove that a certain expression or a certain statement can be divided by a certain, usually an integer number. Now, vectors, we're going to do a review of vectors. I believe you've looked a bit at vectors previously. I'm quite sure. We're going to look at, again, some stuff that you've probably seen before, some operations on vectors, dot product, scalar multiplication, stuff like that. And then we're going to look at sort of vectors in 3D and proofs on vectors, geometric proofs using vectors. Lastly, we're going to look at matrices, and we're going to review matrices. Again, I think you should have seen matrices. We're going to look at operations and applications of matrices. So this should be a 2-hour lecture, if I've planned everything out correctly, covering mathematical induction, vectors, and matrices. If you do have any questions, just ask in chat. Someone, probably me, should be there ready to answer any questions, even though this is a pre-recording. So about me. My name is Vaughan Sampson. I'm a graduate of the Southport School, a school on the Gold Coast. I'm currently studying software engineering at the University of Queensland, which my plan to have started studying that is why I did Specialist Maths, as it's a sort of recommended, or it might even be a prerequisite. I'm a bit of a nerd. I like games design and website programming, reading, and I'm a bit of a political theory junkie as well. So you can probably maybe find me arguing about some nonsense on Twitter or something. If you have any personal questions about me, or just curiosities about university, or the year that you're entering in probably your final year of high school, then feel free to ask me at the end of the lecture in chat. So, for Specialist Maths, my recommendations for Specialist Maths is one, that you try to concentrate on long-term study. I would say for me, and for lots of other students, Specialist Maths is the hardest subject that you will do. Some students find it very easy to sort of accumulate knowledge in some of these other subjects, but more consistently, students have the most difficulty in Specialist Maths, in terms of especially understanding these really complex questions that you can't just memorize. You really do have to get a basic understanding of how it all works. And that will come not just from reading once, usually. That will usually come from really practicing those skills until it becomes sort of fundamental to how you're looking at situations. So, Specialist Maths, I'd say, is mainly built on skills, long-term sort of practice rather than rote learning. That isn't to say that you shouldn't cram. I definitely think, to an extent, having crammed is still useful, like before an exam. If there's still stuff to learn, and there will always be still stuff to learn, you will not many students get 100% in their exams. If there's still stuff to learn, cramming isn't bad, especially looking over all of your work and reviewing before exams how problems that you've seen were solved. So don't memorize answers. You're not going to be able to memorize memorize the answers for specialist maths. That's or probably not for much of your maths. You're really just going to have to understand processes and systems. Now, in terms of challenging questions, you will learn the basics in class, but the really complex stuff in specialist maths, you will probably have to go off on your own and study. So that's something that I would recommend pursuing. Really like finding the difficult questions that you don't know how to do. A lot of them you won't know how to do them. Studying them by when you completely fail to actually make any headway on them, looking at how they're solved and writing down that solution, and then coming back a few weeks later to those questions. That's probably what's going to actually save you from just being completely lost in complex familiar and unfamiliar during the exam. Now, I would recommend as well, it's good to sort of keep a review, like to keep a system of reviewing what you've worked on in the past and your past answers, because you will forget things. You are expected to know things at the end of the year that you are learning now, or some students like last year. So, it's definitely good to consistently have a real habit of reviewing, your past working, keeping your past working, organizing your past working. Okay, so let's begin on the actual concepts. What is mathematical induction? It's a specific method of proving propositions on expressions. So that would be such as 8 divides 8n. That's a very obvious, you don't actually have to use mathematical induction to prove that, but that is a proposition that you could use mathematical induction to prove. That 8 divides 8n, where n is an integer. Another one is that, a certain sum can be modeled by a general equation. And we're going to look at examples of those two, of sums and divisibility. So we often use mathematical induction to prove that a sum can be modeled by a simpler equation or a general equation. Instead of having to add up everything in the sum, you can have like a more basic formula that gets you to the end solution very quickly. Or we prove the divisibility of an expression. Now, the best way to learn mathematical induction is really just doing it. It's not... Once you get the hang of it, and I've done it for a long time, because a lot of you might also do it in university, in discrete mathematics, and maybe some other mathematics courses. So it is sort of a long-term skill for a lot of students that are doing specialist maths now, and you will just get better at it as you do it. You'll get more and more comfortable with it as you go. It's definitely a skill-based, practice-based type of question. So what do you actually do in mathematical induction? First, you do usually a basis step. So what you're doing in the basis step is that you prove true for whatever statement you're trying to prove true for the minimum value. So mathematical induction is done on a type of set that we call a well-ordered set. So a set is just a group of expressions numbers of anything, a group of anything, where each thing is a unique value. So in a set, you can't have two twos. A set of anything, a group of anything. Now, a well-ordered set is a set where there is a true minimum value. So if I said for all integers above 1, then there is a true minimum value because 2 is the smallest possible value. On the other hand, if I said for all real numbers above 0, there's no true minimum value because if I go like 0.0001, I can still go smaller. You can infinitely go smaller and smaller, so that is not a well-ordered set. So mathematical induction, we look at well-ordered sets, where we can get a true minimum value. So we want to prove true for the statement for the minimum value in the basis step. Then we do the inductive hypothesis. Now what we do in here is we assume true for k. So k doesn't really mean anything real. We're just making a statement basically that says this is true for k, And that will start to make sense in the next step, which is the inductive step. So in the inductive step, we basically say, okay, if it's true for k, if it is true for k, then we can prove true. Oh, my mistake. Then we can prove true for k plus 1. Now what this means is we've proven for the minimum value. Then we can say that if it is true for k, k plus 1 is true. So that means we have the minimum value. Let's say it's 0. That means if k, 0, then it's true for k plus 1. So then it's true for 1. Now if it's true for 1, we then know if true for k, it's true for k plus 1. So now it's true for 2. And it sort of recursively proves itself as we move up. And that's what mathematical induction is. So we're going to actually, get an understanding of what all that means by actually, doing mathematical induction. Okay, so let's look at this real example of mathematical induction. We are proving that a sum can be modeled by a general formula. So this says 1 squared plus 2 squared plus 3 squared all the way up into n squared, and n can be any positive integer, it says, is equal to this general formula here. So that's 1 over 6 times n times brackets that say n plus 1, and then times brackets that say 2n plus 1. Now, this is very useful in mathematics because, okay, let's say we wanted to find the sum of 1 squared plus 2 squared plus 3 squared all the way to 10 million squared, as an example. Instead of manually having to actually figure out each one of these and add them up using a calculator, of course you could use a computer to do it, but it's much more cheap in terms of time, even for a computer, to just use this general formula instead of doing 1 million operations, 10 million operations in this example of squaring and then adding all of those operations. Instead, we just do one single expression that explains basically all of those 10 million different terms. So that's sort of the use of mathematical induction with sums. Now let's do mathematical induction. So first what we're going to do is we're going to basically rewrite the statement, and you'll get very bored of rewriting the statement because you're going to be rewriting the statement at least slightly different each time, a lot, during mathematical induction, but it's an important part of the process. So when you write a mathematical induction, it's sort of like, think of it like you're writing a single article, a single item. It's supposed to stand on its own two legs. You're not really writing it as though the marker knows what the question is, even though they do know what the question is. You're writing it more like an academic who is trying to write something that any mathematician could read without actually knowing the question and just understand what it's proving. And that's generally what we do for proofs. So that's why you rewrite this formula here, and this time you write it, or this set of expressions here, and this time you write it as let Pn be the statement 1 squared plus 2 squared plus 3 squared or plus plus n squared is equal to, then we have this general formula right here. So we rewrite basically what we're trying to prove. So now we're going to do the basis step. Now you don't really have to write basis step and induction hypothesis and such. It might be good to, it's your choice, it might help the marker a bit, but this is what I'll do to sort of give you an understanding of the process that we're going through here. So the basis step. Since we're in a well-ordered set, we can have a basis step where we use the minimum possible value. So in all the positive integers, the smallest value is 1. It's the smallest positive integer. So we should probably actually write something like consider P1. There you go. Consider P1. What does this culminate in? This culminates in 1 squared plus 2. 1 squared, sorry. Then we don't go any further because n is 1 here. Equals 1 over 6 times 1 plus 1, 2 times 1 plus 1. So that equals 1 equals 1 over 6 times 2, 3, equals 6 over 6. So left-hand side equals right-hand side. Therefore, we have our proof just of P1. Now we have to prove that it is true for pk plus 1, where k is anything that we've already proven, basically. So that means if it's true for 1, which we've already proven, we can know that it's true for 1 plus 1. Now that means we know that it's true for 2, which means we know that it's true for 2 plus 1, and we have this recursive proof that we're building. So let's do the inductive hypothesis. So this is basically an assumption that we make that it is true for pk. The reason we assume that is because then we can next say, if it is true for pk, whatever integer k is, whatever positive integer k is, if it is true for pk, then it is true for pk plus 1. That means we have our recursive proof. So let's do it. Let's say assume true for pk. i.e., so that is that 1 squared plus 2 squared plus 3 squared all the way up into, this time, k squared is equal to 1 over 6 k plus 1, 2k plus 1. Okay. So it's basically the same. We rewrite this once again. This time we use k because we want to separate it from n. We don't really want to assume that it's true for n, because if we did that, we're assuming that it's a little bit dirty looking, I guess, because we're assuming that the statement is true to prove that it's true, which is a bit absurd. So we just give it sort of a level of separation by putting k in there instead. And that's the induction hypothesis. Now we're going to do the inductive step. So we're going to consider pk plus 1. So we're going to consider pk plus 1, and we're going to use our assumption of pk to prove pk plus 1. Now we're going to do that on the next slide. It's probably going to be doing a little bit of going back and forth, unfortunately. Let's consider pk plus 1. So that is, we have 1 squared plus 2 squared plus 3 squared plus ... all the way into k squared plus k plus 1 squared. Technically, you wouldn't have to write this down, but it's good to write that down because it sort of keeps a connection with our assumption that we made for pk. And you wouldn't have to write it down because if we go all the way to k plus 1, then we can assume that k squared could be in the ... if we didn't write it down. So then we're going to say that equals to 1 over 6 k plus 1, because we're going to basically just put k plus 1 everywhere where there was a k plus 1 plus 1, 2k plus 1 plus 1. So now what we want to do is we want to figure out a way basically to get some components of this whole equation here. Oops. And if we can equate those components, if we can get some of those components and we can equate some of those components to something in here, we might be able to create a proof. And as you do induction, you'll sort of get a hang of this process. Somewhat, you're going to have to learn to actually build an intuition for this, to be honest. That's why this is, like, I think more than any type of question you're going to do, this is a very practice-oriented type of question to learn. But our example still stands. So now what I'm wanting to do is I'm going to concentrate on the right-hand side. Since I want it to sort of look, I want to basically get some component of this over here in here, I'm going to try to keep some things. So I see there's k plus 1 here and there's k plus 1 here. So I'm going to try to keep that. I'm going to try to build this whole right hand side as a component of this right-hand side here. And we'll see where that actually gets me soon. So this is k plus 1, k plus 1 plus, we'll just change it to 2, and then 2k plus 3, all over 6. So now I want to keep the k plus 1, but I want to expand these brackets on the right here. Say 2k squared, so that's k times 2k, plus 3k, plus 2 times 2k, so that's 4k, plus 2 times 3, which is 6, all over 6. And I'm going to simplify it a little bit. K plus 1, 2k squared, plus 7k plus 6, all over 6. Okay. So I'm already starting to see some patterns that remind me of this situation over here. So we have the 2k plus something. This time we have 2k squared. So if we were able to take the k out of this over here, we would be benefited because we'd be able to put the k at the front. And basically, we're looking for patterns that we can try to replicate through challenging algebra. So I'm going to, a lot of the time when you're actually doing this on an exam, you will be writing lines and lines, and then you'll realize that they got you nowhere and you're going to cross them out. This is a pretty simple induction. I've seen it before, so I'm a little bit advantaged by partly remembering the process. But don't be discouraged if you try to move things around and it doesn't immediately get your result. That is what you should expect. You're going to have to try to move things around a lot in specific ways until you find something convenient. If you're really stuck, maybe consider that you've made a mistake earlier, so it's completely impeding you from moving forward. And that is something that's really punishing about induction questions. It's really hard to get those carry-through marks because you can't finish at a proof if you've altered the statement so it isn't even actually true. So there's challenges there. But here I'm going to try to... So I want to get a k. I want to take the k out over here. I'm not going to be able to take the k out of this set of brackets because there's a 1 there. I'm not going to be able to take it out of this set of brackets yet, but maybe I could remove, and I want to keep that 1 there to be clear, but I don't necessarily want to keep this 6, and I don't want to keep this 7k because they don't look anything like anything that I have in this equation over here. So I'm going to play around with things a little bit. I'm going to say plus k because over here we do have that plus 1, and remember I want to take this k out of this set of brackets, so everything's going to be divided by k. And then we have plus 6k plus 6, all over 6. Now I can remove these from the brackets. If I go k plus 1, 2k squared plus k, all over 6, and then I can remove these. Let's put them in their own brackets for a moment just to make the working easier. I can remove these to their own set by multiplying them with everything in the other sets of brackets. So that becomes 6k plus 6 and then multiplied by k plus 1. So maybe just look at it for a moment if you're a bit stuck with that, but these are actually equal. I can basically take this out if I multiply it by everything it needs to be multiplied by. So now we have these two sets. Now, if we go up here and work it out a little bit more, we can take the k out of this set of brackets now, which is what I was trying to sort of move towards. So then we end up looking like this, over 6, and then we have a plus, and then we can take 6 outside of these brackets, so it's a 6, k plus 1, k plus 1, all over 6. So then this equals to k plus 1, 2k plus 1, all on 6, plus k plus 1 squared. So this is where we want to be. We basically have this left side over here, this right side, sorry. We've created that. That's the same as this. And then all we have is an extra k plus 1. So then I can say equals, since we have this right side here, remember this right side is equal to that. So then I can say equals 1 squared plus 2 squared plus 3 squared plus dot 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 plus k squared, because this side is equal to that side, and then we have this extra plus k plus 1 squared. And now our equation actually looks exactly like this over here. So our proof is done. We have left-hand side equals right-hand side. So it can get pretty hard in the middle, but I think it is a situation of, if you practice these a fair amount, you will start to get a sort of intuition, a sort of sixth sense as to how we can actually move towards a solution here. Basically, and we'll see this when we do the mathematical induction for division, we use this assumption of pk to prove pk plus 1. So now that we've proven left-hand side equals right-hand side, we will write something of this form. Some teachers teach you a really specific way to write it that you can just memorize, so it's easy. I'm going to write it like this. We have proven Pn is true for P1, and if true for our assumption, which is pk, then true for pk plus 1. Therefore, we have proven by mathematical induction. Okay, I'll do it like that. So basically, this just is a little thing that you should always put at the end of mathematical induction to explain what the process is. You said, okay, we have proven that it is true for 1, and we have proven that if it is true for any value of k, if it is true for that value of k, such as 1, then it is true for k plus 1. So we have proven for 1, therefore true for k plus 1, which is 2, because 1 plus 1. Then if it is true for 2, then we have proven for k plus 1, so it is 2 plus 1, so it's 3. So we've made a proof that, recursively proves itself for infinity, which is a very beautiful thing. So now let's look at how to utilize this mathematical induction to prove the divisibility of an expression. So this example here is show using mathematical induction that for any value of n, that is a positive integer, 7 to the power of 2n plus 16n minus 1 is divisible by 64. So let's first, using our mathematical induction rules, like we're using a very similar process to what we just used before. There's just like a few little steps that might help you sort of change how we're doing things a little bit to understand what is the general process of finding the proof, finding how to prove divisibility with mathematical induction. So let's first say let Pn be the statement that we can write it like this as well. You might not know, but we can use a vertical bracket to, sorry, not a vertical bracket, a vertical line to say that 64 divides, that is 64 divides 7n plus 16n minus 1. So we rewrite the statement, and then we do the basis step. We're following a very similar sort of system to last time, and that is the system of mathematical induction. Let's consider P1, because that is our minimum value of our well-ordered set of the positive integers. So we have P1, that is 7 2 times 1 plus 16 times 1 minus 1, which is the same as 49 plus 16 minus 1, which is equal to 64. So for our basis step, we know that it's true because 64 divides 64. Therefore, it is true for P1. Then we can do our inductive hypothesis. So we're going to assume true for pk, i.e. Now, with this inductive hypothesis, with divisibility, we can first we can write sort of the same form that we did up here for n, but then we can write this same statement in a different form that's much more helpful to us. So we have 16k plus minus 1. Therefore, we can write this statement in a different way that says 7 to the power of 2k plus 16k minus 1 is equal to 64m, where m is an integer, is any integer. Now, what this is saying is this is basically the same statement. This is just saying that 64 is a factor of this, which is the same as saying 64 divides this. So based on this, we can finally do our inductive step. Now we may as well do this on another slide. Step. For that, we are going to again consider pk plus 1. So that is 7 to the power of 2k plus 1 plus 16k plus 1 minus 1. So we want to prove that this is divisible by 64. Now, that means it equals to 64. This time, let's say n is a very bad one to do. Let's say t, where t is in integers. So we're going to basically try to prove that this is true. We're going to consider it. Now, to do that, I'm going to write out, I'm going to sort of expand this right side here to simplify our expression a little bit and get us just a bit closer towards finding an answer. So what I want to do here is I'm going to want to basically be able to, again, like last time, like we did over here, where we were able to substitute this into our equation to get an answer, to get a proof. We're going to want to substitute this into our expression here, and therefore we can get a 64m. And that is obviously divisible by 64, and then whatever's left should also be easily divisible by 64, because that's just how it tends to work out in these proof by induction of divisibility. So I'm going to keep expanding this out to make my life a little bit easier. That's times 7 squared plus 16k plus 15. Now that means we have a 49 times 7 to the power of 2k plus 16k plus 15. So since I want to basically have this expression here as part of this expression, I'm going to look at the easiest way to do that. And from my perspective, the easiest way to do that is to get a 16k and a minus 1 inside these brackets here. How do I do that? Well, and this is generally how the step that you're probably going to have to do for these proofs of divisibility. You're going to go write the equation down, and then you're going to add, since you want to get something in these brackets here, you're going to, let's say we want to get 16 in these brackets. How are we going to do that? Well, it's useful for us to add 49 times 16k, and then also subtract 49 times 16k. That means that what we can do is we can actually, since 49 is a factor of this, obviously, we can move the 16k into here, into these brackets. And then we have this on the outside, but we can worry about that later. Now we also want to get a minus 1 in there. So I'm going to do a minus 49 and a plus 49 at the end as well. So the equation is still equivalent. The expression is still equivalent to this expression over here. They're equal to each other, but we've put it in. We've added some factors. we've added some parts, some terms that can allow us to move things around a little bit. So we have 7 to the power of 2k minus plus 16k, because I've moved the 16 in there. That means we can cross out all of that. Minus 1. That means we can cross out this. So then I have to write everything that still exists on the outside. And now we're at sort of a slightly better spot, and I'll show you why in a second. It's 49. Okay. So now what we can do is we have this here, which is exactly the same as this expression here. And we know that this expression is equal to 64m. We know that it's divisible by 64. So we can put 49 times 64m. And it's still equal. So we have plus... Now we can move sort of these terms together. So we have a 16k, then we have minus 49 16k. So that equals to minus 48 times 16k. And then we have a 15 plus 49, which conveniently equals to 64. Now we have 64 outside of 1 from this value over here. And then we have plus 49m. And then outside here, we just have a minus 48 times 16k. Now, what I'm going to do with this is first I'm going to move it all the way up here. I'm going to divide this by 4 and times this by 4. So that leaves us with 64, 1 plus 49m minus 12 times 64k. So we can put everything in these brackets here, with these brackets with 64 on the outside. 49m plus or minus 12k. Now, this point allows us to immediately say everything must be divisible by 64, obviously, because we have that on the brackets outside, and m and k are both integers. So that means we have 64 divides 7 to k plus 1 plus 16k plus 1 minus 1. Now, that means true for pk plus 1 if true for pk. And that's because we did use our assumption we made over here of pk to then prove pk plus 1. So then we can write out our final statement that we have to do for every mathematical induction. It always gives you a mark. Even if you can't figure out a mathematical induction, if you can just like sort of cheat and write this statement without actually ever getting an answer, like write something like this, you can often get half or a full mark in an actual exam. So we're going to write, we have shown true for n equals 1, sorry. And I'm writing it in a very different way than I'm doing it over here to make a point that you can write it in quite different ways, because it is just a statement that summarizes what you've done. So we have shown true for n equals 1, and if true for n equals k, then true for n equals k plus 1. Now, it would be good to write at the end, we have therefore proven true by mathematical induction. But I'll just do that. So that is our system of mathematical induction. It's complicated, and a lot of it just comes down to doing a lot of these questions over and over until you realize there are it sort of becomes intuitive, I guess, how to do them, because they are actually fairly surprisingly consistent how to achieve them. Like most of these divisibility questions, you're probably going to have to do what I did here. Basically, add these terms in so that I can put something into factorize something into these brackets here. So there are consistent methods of moving towards answers for these mathematical induction questions that you will only get good at when you have actually spent a fair amount of time doing these questions. They are questions that you will mainly learn, and you might not necessarily understand immediately, but the more you practice them, the more they will just sort of, the process will start to make sense to you. And I would say that more than any other type of question, basically. I'd say more than any other type of question in specialist maths, I think mathematical induction questions require practice and not just like an understanding. So now let's move on to our second topic, which is vectors. A vector is a quantity defined by a magnitude and a direction. So you can't really get a vector confused with coordinates because they're quite different. A coordinate is a place. A vector doesn't care where it is. It just cares the direction and magnitude that it moves in that direction. So we like to represent vectors with arrows, where the length would represent the magnitude and the direction would be represented by the way that the arrow faces. So let's say if it's on a plane, the direction we could think of as like maybe the angle from the x-axis, which is a very common way to consider the direction of a two-dimensional vector. Now, two vectors, that means two vectors are equal, not based on their initial position. They don't have an initial position that actually defines them. You could place them from somewhere if you wanted to, like with some geometric questions, you put them somewhere, but we would consider them equal to another vector if their directions and magnitudes are equal. That means, let's say I have a shape that has positional points. Let's say I have this shape here. I have A, B, C, D. The vector that we can say is from A to B, and we write it like this, is the same as the vector from C to D. I'm sort of assuming with this shape, this sort of rhombus, I guess, that C to D is the same length, and that they are parallel to C to D is the same length as A to B, and C to D is parallel to A to B. If that's the case, these two vectors are the same vector. They are equal because they have the same direction, they have the same magnitude. So we like to write a vector from between 2 points. Let's say it's from A to B as such, like this, A to B. We can also just give a vector a value like this, though. We can just say A to B equals A. We can just give it a variable like anything else. Now, the magnitude of AB, we would usually write this. We use two vertical bars, and we put it outside of the vector. So we could do it like this as well if the vector is A. Now, a unit vector is any vector with a magnitude of 1. These are useful for some specific types of questions and problems that we like to solve. So let's look at the multiple forms of which we can write vectors in. So we have something called column form or matrix form. Basically, for this and component form, we split up what a vector is into components, into parts. So for column notation, instead of writing a direction and magnitude, we describe it, if it's a 2D vector, we can describe it with two magnitudes. So we can describe a vector with two magnitudes if it's a two-dimensional vector, let's say A and B. And for example, we could say 3, 1. Then if we were to plot this on like a plane from the origin, we would say probably looks something like this, because it moves to the position 3. It points towards the position 3, 1 on this plane. Component form is quite similar to this, except we separate it into these components. We write it like this. So this is a two-dimensional vector as well. We have 3i plus 1j. J is basically the direction along the component. J is the component which moves along the y-axis, whereas I is the component which moves along the x-axis, if you were to represent these on, say, a Cartesian plane. Now, polar form represents a vector more so as what it is. It represents a direction and a magnitude. So that would be magnitude first and then direction. The direction, if we're thinking in terms of like a Cartesian plane, we would usually represent the direction as being an angle anti-clockwise around the from the x-axis, sorry. So sort of moving like this, and then whatever angle that is the angle of our vector. And the magnitude is obviously, again, the length. So in this scenario, the magnitude of this would be 3 squared plus 1 squared, and then the square root of that, because we could draw it as sort of a triangle and use Pythagoras' theorem to find out what is the actual length here, what is the magnitude of that. So let's actually do a question where we convert between forms of interpreting this vector, because that can allow us to get an understanding of what is polar form relative to component form. And this is useful because some problem-solving questions, it might be useful to interpret a vector in a different way. So, to convert A, which equals to 12i plus 4j into polar form, we want to consider its magnitude and its angle. We can use Pythagoras' theorem to find its magnitude. So, for example, this is a pretty simple. Do remember to, if you're drawing a triangle, let's say this was negative, do remember that you should draw it like this to not confuse yourself, because we're thinking in terms of we're on some sort of set of axes, and if the I component is negative, we need to move backwards along the x-axis. But for now, we just have 12i plus 4j. So I can put a 12 down there and a 4 there. And then we have the angle in here. And then we have the magnitude up here. So the magnitude, based on Pythagoras' theorem, will be the square root of 4 squared plus 12 squared. And the angle will equal the inverse tan of 4 divided by 12, because that is opposite over adjacent of the angle. So I can quickly use my calculator to find that m is 12.65 based on this, and that the angle is 18.44. So then our polar form can be written as 12.65 and then 18.44. And of course, we can't remember our type of angle we're using, because often we might use radii. So radians, sorry. Now let's consider some simple operations on vectors. So we have addition first. Now we should note that addition is commutative. That means b plus a is equal to a plus b. That doesn't matter what order you put them in. If it's just addition, it's the same. We can prove that by looking at arrow representations of vectors. So even if over here we have a goes first and then b goes first, and then you can see the final line that it generates, which is a plus b. Instead, we can put b first and then a, but then this final line looks the same. So we have a commutative sort of operation here. Now, vector subtraction is sort of a little more interesting to look at. If we subtract b from a, we get the vector that goes from where b ends up to a, if they started at the same location, if you place them sort of geometrically like that. So that means it isn't commutative. A minus b does not equal to b minus a, because let's instead do this line as b minus a. We have a and b. Now b minus a goes in the opposite direction. So it might have the same magnitude, but it doesn't have the same direction. It actually has the direct opposite direction. So they are not commutative in terms of subtraction. Now, scalar multiplication is pretty simple. When you multiply a vector by just a simple magnitude value, all you do is you multiply its magnitude by that value. Direction doesn't change at all. So if I said, if I have this line, and then I multiply this line by 2, you could just imagine it gets 2 times as long. And that's what scalar multiplication is. So if I have k times a, and a is a vector, then the magnitude of that will be the magnitude of a times k. Of course, as well, you can multiply vectors by a negative scalar, and then they will go in the opposite direction. So that is actually the one instance where direction does change. I should be clear about that. You can multiply them by a negative number, and then it will go in an opposite direction, but you can't change the direction other than flipping it. So let's look at actually doing some addition using component form, which I would say most operations that you're going to be working with, component form, or you could also put it in, column form, matrix form. These are the easiest forms to operate in. So A is equal to 10i plus 5j. We could try to represent this as sort of like this line here, where we have 10 across and 5 up. And then we have B is 5i minus 10j. So we could represent this as sort of a line going down here, where it goes 5i across and then 10j down. So A plus B is equal to simply all of the components added together. So we can make this very easy on ourselves if we're using component form. Polar form would be a lot more difficult to recognize, like how to find a solution. So that's 15i minus 5j, and that's our answer. Now let's do this for this question down here, but let's use matrix form instead. So if I was to represent A in matrix or column form, I would say 12 and then 4. And then we have, so that's A equals, and then we have B equals 6 minus 3. So if I want to subtract B from A, that would be the vector that goes between that goes from B to A. So we can simply do it like this. We have 12, 4, minus 6, 3. And then we can, of course, use our normal understanding of maths to interpret it as we can flip it to a plus, and then we can flip all the signs inside these brackets here. So then the resulting matrix vector would be 6, 7. And that would be, this is the line that goes from B to A. This is the vector, sorry. So what is the vector from A to B? To do that, we should do B minus A. So 15i minus, 4i minus 15i. Then we have minus 9j minus 4j. This all equals to minus 11i minus 13j. And that's our answer. So we can also have vectors with more dimensions. The highest we often actually work with, because we're often thinking of our physical reality we live in, is we work with vectors in 3D. Now, all the same forms can apply, they're just a little bit extended each time. So for matrix form, we just have one more value down here. So we have A, B, C now. So we have a C instead of just two values that we were utilizing at this point here. And then we can like addition, subtraction, scale, and multiplication works pretty similar. You just do it on all components as opposed to two. On three components as opposed to two, sorry. Then in terms of component form, we use I plus J, and now we just add another one. We use K. Then in terms of polar form, we can just add one more angle, and then we have a solution. So if we were just on the x and y axis, let's say we had a line going down here, it might look sort of like this, and then there's our magnitude, and then there's our angle. But instead, we actually have a line going up here now into like 3D space. So then, if this sort of goes up to there, if this line in 3D space is directly above that line, all we have to do is we have to add this angle in here, and that will probably use a different symbol. If we should add an angle in here, and that will, let's use this symbol. We'll add an angle in here, and that will work with everything. So that means we have M, this symbol, and this symbol, and they represent angle 1 and angle 2. So this is the angle clockwise from the x-axis, from the direction of the x-axis, and this would be the angle from the direction of the z-axis. So we're going to work with addition and subtraction with these 3D vectors. Now this is 3i plus 1j, so that's our normal 2D. This is 5j minus 1k, so that is like in our 3D space now, because we're moving up the z-axis with that k involved as well. Then we have c is a minus b, d is 3i, so that's a full 3D vector with all three components. So what is the vector from D to C? So first we'll figure out what C is. So C is equal to A, 3i, plus 1j. And that's minus B, so that's minus 5j minus 1k, or plus 1k, because we're flipping the sign. So C is equal to minus 2i plus 2j. So then D is equal to, so we want to get D to C, so that means we're doing C subtract D. So that equals to minus 2i plus 2j, and then we subtract everything in D. So this is all quite simple. It's just very basic addition, subtraction, etc. Okay, so that's our answer. Now we could put that in other forms, but I think we'll do a question like that soon. For vector A and B, the dot product is A dot B is equal to the magnitude of A times the magnitude of B multiplied by a cos of the angle between those two vectors. So the dot product is something we use to interpret basically the relationship between two vectors. Sometimes we can use it to prove that the direction of these two vectors are perpendicular. And the reason we can do that is because it gets multiplied by a cos of the angle. And if the angle is 90 degrees, then the cos of the angle is 0. So it comes out that they're perpendicular. Now you might think, oh, so we need the angle to prove that they're perpendicular, but if we already have the angle, we know that it's 90 degrees. But not necessarily, because there's multiple ways to find out the dot product. So sometimes there's ways to find out the dot product without actually having the angle. And that's what we're going to look at sort of soon when we work with the dot product in multiple different ways. So this makes vectors used very often in geometric proofs when you have to prove things are perpendicular. That's because it's very useful to use the dot product here. So let's look at finding how here it is found the dot product between these two vectors. So what is the dot product of A dot B? Now we're going to do this in polar form because this helps us because we want the magnitude of each and then the angle between them. So that means we need their polar form. We have their polar form here that's been figured out. That's based on A is sort of like this, where there's 3 and then 1. So then, the magnitude's up here and the angle's up here. So that finds this value here. And then B is equal to sort of like this. We go 1 down and 5 across. So then our angle we can do it as negative, or we could also do an angle all the way around this way until we get to here. So then we find our magnitude, whatever. We have the polar form. We've been through how to get it. We just use trigonometry. Now that we have it, we can actually apply it. We can do 3.65. So that's a magnitude times a magnitude, and then times the difference in angle. So the difference in angle would be, if you get the difference between 11.31 and 18.435, that would be 18.435 minus 11.31, which is equal to some value that I'm not going to immediately come up with, somewhere around 30. And then when you plug all this into the calculator, as you will often be doing with the dot product, you will come at the result that it is 14. So that's the process of doing this, of finding the dot product if you're using polar form, but there's a much easier way to do it that I think is a lot more useful. So what we can do, instead of actually knowing what the angle is, we can use component form to find out what the dot product is, and then we can sort of understand what the angle would have been. Basically, like if it's perpendicular, the result is 0. We can understand what the angle would have been without actually finding the angle. Or like understand if the angle is something special, basically. Is it perpendicular without actually finding the angle itself? So if I want to get the dot product of A and B, what I can do is I can just multiply each of their components and then add the sum of all that together. So here we have A is equal to, let's say A is equal to 1i plus 2j, and B is equal to 4i plus 3j. Then the dot product of A and B we can very quickly find by we just do 1 times 4. That's multiplying these elements. And then 2 times 3. That's multiplying those elements. So our result is 10. So if we ever do this and we get a result of 0, that means we know the angle must be 90 degrees. Because the result must have, because the other form, if we went in polar form, we would have found that the angle between them was 0. Or was 90, sorry. 90 degrees. Now, what is the vector dot product of A dot B? Let's actually do these questions. Oh, there's already an answer here. So we have 3 times 5, 1 times minus 1, and then you find that the result is 15 minus 1 equals 14. So that's sort of the same as what we did up here. It's the same actual set of vectors, and it comes up with the same solution. So understanding that you can do the dot product this way will help you with some proofs, and it will help you simplifying your working instead of having to convert to polar form every time, which takes a lot of time. So let's find the dot product of C and D, and it really saves time when you're having to work in 3D space. So the dot product between C and D equals 10 times 2, that's this group here, minus 3 times 12, plus 3 times 4. 20 minus 36 plus 12. 20 minus 24 equals minus 4. And that's our dot product. So let's use vectors to look at proofs. Geometric proofs that you don't have to use vectors for all types of geometric proofs. It's just one way of interpreting them, and specifically given things like the dot product, some properties of vectors, it can be very useful to use geometric proofs. So we want to prove that the diagonals of a rhombus are perpendicular. Now, that means we should look at a rhombus and note a few things. Okay, so we have this rhombus here. D, A, B, C. Now, we should note that the opposite sides of a rhombus are parallel, and that every side of a rhombus does have the same length. So that means any vector we can make, like if we did the vector A to D, it will have the same magnitude as if we did A to B, because every straight side has the same length. So what we want to prove is that the diagonals of a rhombus are perpendicular, which is a good place to use vectors because we can use the dot product. So we want to prove that these two diagonals have a 90 degrees in there, basically. So we're going to go to a blank page. We're going to do D, A, B, C, of course. We should plot everything Okay, so now we can start working with these values. This here gives me a little hint to work with AC and BD. I'm not going to put them in terms of B and D because I think it might confuse things a little bit. It might be better if we just work with the basic descriptions of sides. So we want to prove that this here, and let's make this a vector, this line is perpendicular to this line. They travel in perpendicular directions. We want to show that it's 90 degrees there. So let's actually put these two vectors in terms where we can actually relate them to each other. So if we want to do A to C, let's first just put it in the terms of AB plus B to C. So we're saying we go along this side and then along that side, and that's where the vector ends up. We can add them together, and that creates the vector A to C. Now we want to look at B to D. So we can put B to D in terms of B to A, and then plus A to D equals B to D. So that's going along this way and then down that way, and that finds our final vector there. So now that we're here, we can start relating, making these two look more similar to each other so that we can work with them, cancel things out and such. So let's look, okay, A to B and B to C, let's keep that. Now, B to A is actually the same as negative A to B. So we can say this actually equals the same as negative A to B. Plus A to D is the same as B to C. So A to D, because it's the same magnitude and it's parallel, so it's the same direction. So we can put this in terms of B to C. This should be B to D. We can put this in terms of B to C. Now, where we are now, we have these two quite, seemingly related terms here, because we have B to D equals B to C minus A to B. We have A to C equals B to C plus A to B. So we can immediately see where there's probably sort of getting somewhere in terms of relating these using the dot product to find something. So now that we have these two lines, let's dot product them together. So we do B to C minus A to B dot B to C plus A to B. Now we can sort of expand this in the same way we would multiplication. So we will say, we'll expand everything into B to C dot B to C, and then positive B to C dot A to B, negative A to B dot B to C, negative A to B dot A to B. Now, we should note that multiplication of the dot product is commutative. That means that these two are actually the same, or these two are the opposite, sorry. So this is the same as that. That means we can cancel these two out because this is subtracted by that. So we end up with B to C dot B to C minus A to B dot A to B. Now, when we do the dot product, we know that we end up with a magnitude. Now, the angle between A to B and A to B will, since these are actually opposites, it's minus A to B and A to B, we know that the angle between them will be like cos 180, which is 1, or negative 1. So, since we have a negative 1, multiplied by, we should probably write out the dot product. So A dot B equals A, B, cos the angle. So with this, we end up with the magnitude of AB squared, magnitude of AB squared times minus 1, because cos 180 is minus 1. They go in opposite directions, so the angle must be between them 180. And then BC, dot BC, is a similar thing. It's the magnitude of BC squared. This time it's times 1, because what we have is we have cos 0. The angle between these two same vectors is 0. Here, now we realize, we go back to what we learnt before, and we realize the magnitude of each of these lines is actually the same. So we know the magnitude of A to B is the same as the magnitude from B to C, because each side of this rhombus have the same magnitude, of the same length. Based on that, now all we're actually doing is we're just doing BC squared minus AB squared, which equals 0. So the dot product equals 0 because the magnitudes of all these sides are the same. Therefore, we've completed our proof. If the dot product is 0, then we know that the angle between these two lines must be 90 degrees. So we'll look at a more complicated sort of proof here. Prove that the diagonals of a parallelogram bisect each other. So let's think about what a parallelogram has. We know that these sides are of the same length, these opposite sides. And we know these opposite sides also are parallel. And now we want to prove that the diagonals of the parallelogram bisect each other. So what is the mathematical statement that we want to actually prove? I would say we want to prove that the position of, I should be clear actually, bisect, if we haven't covered this before, it basically means if a line is bisected, it means a line is cut into two equal pieces. So if these lines bisect each other, that means they intersect at the point in which they are both halfway in length. So we want to prove that. So the mathematical statement we want to prove is we want to show that this point of intersection is the halfway point of both of these lines, is the halfway point of A to C, and is the halfway point of B to D. So we're going to quickly draw our shape again. Trying to prove that in the middle they're halfway. So we're going to pick an origin for a question like this. Unlike this question over here, where we're concentrating on, we're trying to prove something about the direction. Now we need to prove something about a position. We want to prove that the position in which they are both halfway matches. It's the same position, therefore they collide, they overlap, they intersect at that halfway point and chop each other in half. So based on that, let's look here. Let's use A as an origin position, a position which we consider everything relative to. So that means A to D, we're going to consider as just A to D. The position of halfway A to D, we're just going to put as this. Now the position of B to C, we're actually going to do A to B plus halfway B to C. The reason we're adding A to B is because since we're doing everything, we're trying to find a position relative from A, we need to move to B before we can go halfway down this line, to actually consider everything in terms of A, in terms of the position of A, to think of everything relative to the position of A. So we have, what we want to prove is we want to prove that A to B plus half B to C is the same point as half of A to D. So let's sort of follow a similar pattern that we did over here, and let's put everything in terms of these straight lines on the sides so that we can sort of maybe figure something out, cancel something, etc. We could flip. We'll use C and D in this order from now on. I've sort of flipped it over. So let's put A to D in terms of A to B and A to C. So we can go A to D. Let's say half A to D equals half A to B plus A to C. And that's because we can move this amount this way and that amount that way, and then we'd end up at D. Now we can say A to B plus 1/2 B to C is equal to A to B. We're happy with that because that's already like the length of a side, and we're just trying to get everything in terms of the sides. Plus 1/2. Now, B to C is like A to C because we go down, and then it's also like negative A to B because that would move us, negative A to B moves us this way, and then A to C moves us down, so the overall line is like B to C. So we've put everything in terms of these lines, and then we can maybe start to see how we're getting somewhere. So we have 1/2 A to D equals that, and now we can figure out this. We can do 2/2 A to B plus 1/2 AC minus AB. So what this does, this allows us to move this AB into the brackets because we want to get this side, this expression to look like this expression. If they look exactly the same, if they're exactly the same, this proves that these two positions are exactly the same. So we want to move this AB into these brackets, becomes 1/2 AC minus AB plus 2AB. Put our vector lines on top, and that ends up creating A to C plus A to B. And there we have it. We've turned this here into that, because that equals this, and this equals this, and they're each the same. So we've proven that the position in which both of them are halfway, and we're looking at that relative to the origin of A, the position in which both of those vectors are 50% are halfway is the same. Therefore, they overlap, they intersect at that position and then bisect each other. So this is basically the same proof we're looking at here, but we're doing it for 3D space. So for the parallel piped below, prove that diagonals OF and CE bisect each other. So I'm going to use O as the origin this time, and we're going to follow a very similar process. So we want to do OF. So O to F, let's put OF, and we're going to go half of OF because we want to find where they bisect each other, so that's the halfway point. Halfway of O to F is equal to O to A plus O to C, or half of O to A, put all that in brackets, plus O to C, plus O to D. So what that means is we went this much this way, this much this way, and that much this way, and that ends up creating a line that goes from O to F. Now, since we're using O as the origin, and we want to consider C to E, we're going to first consider, we're going to make it so it's O to C plus halfway from C to E. So that means we're interpreting the position relative to O, or we go up here, and then we go halfway down there, which is the same, and on this side, half OF, we're going halfway this way, and we want to find that they're the same point. So we have O to C plus half C to E. What's this equal to? This is equal to O to C plus half O to A plus O to D minus O to C, which equals to, same as last time, we can simply multiply this by 2 over 2, which makes it the same thing. And then we can give ourselves an opportunity to move this into the brackets, to move this OC into the brackets, and that will culminate in half OA plus OD plus OC. And that's the point we end up with. So then we've proven OF is equal to half of OF is equal to OC plus half of CE. Therefore, they bisect. So with these geometric proofs, I've went over the very simple common ones that you will see around. They get much more complicated than this. It's a situation of, I think, looking at the solutions to a lot of these when you get completely stuck, and sort of memorizing them, because if you do look at the solutions and memorize them in a way, it does help you. If you memorize the process to creating a solution, the process to proving it, then you sort of build on your tools, on all of your techniques that you know how to use to move towards one of these proofs. They can be quite difficult, and they do require a bit of an understanding often of the shape you're working with. So if you do get into an exam and there's a question relating to some shape, try to start interpreting what sides are parallel, what sides have the same lengths. Start looking at even the formulas that you might be given in your formula sheet for different shapes, and understanding the shape and looking at that will give you a chance to figure out a proof if you're stuck. There are some absurdly difficult ones that do require you to just look how they solved it to sort of understand. It's good to understand because it'll broaden your skills in terms of solving geometric proofs in general, but don't feel down if you can't immediately do something and if you have to look at the answers, because they are quite difficult. So I would say copying work solutions to get to understand their processes, seeing how proofs are done. If you can see that enough, you might be able to replicate it. Okay, so now we're moving on to topic 3, our final topic. So this is matrices. A matrix, at least the matrices we work with, is usually a 2-dimensional array or sequence of items. Now, these items could be numbers, expressions, letters. You could have a matrix that looks like this of letters. You could have a matrix that looks like this of numbers. This is almost a 1-dimensional matrix because it only has sort of one direction through it. Now, what do we use matrices for? It's sort of like think of it like a sort of mathematical structure that we can use for modeling certain things. We can use it for modeling competitions, solving simultaneous equations, and doing transformations with data and working with vectors. Sort of a higher level thing that is used in very high-end mathematics, even cryptography and such. So let's look at how we do some operations on these matrices. We can represent a matrix sort of like, let's just give it usually a capital letter. I don't really ever see a lowercase letter. We give it a capital letter and we say this equals, and then we define the matrix. So let's do this matrix. Now, when we multiply a scalar by a matrix, we simply have to multiply each of these items, each of these elements inside the matrix by that scalar. And that's all we have to do. Oops, my mistake. Now, this is commutative when you multiply scalars. When you actually multiply 2 matrices, it's not commutative. So we'll go over soon like how complicated it can get multiplying 2 matrices. This does not equal this. If A and B are matrices, A times B does not equal B times A. On the other hand, A times K does equal K times A. And this is sort of used in algebra as well, because we might have like A times B equals C times D. If we want to divide both sides by A, what we do instead of that, if we're thinking in terms of normal maths, we multiply both sides by the inverse of A, and we have to think about the order we do things. We tend to put the inverse at the front. So you sort of have to understand these patterns that we use a little bit to actually make our matrix multiplication make sense, because it is very fussy as to which order you put it in, and you'll get used to sort of the order that you're supposed to put things in. So there's 2 by 2 matrix multiplication. I'm going to go straight into doing 3 by 3 or something of that level. Actually, I might start a bit smaller, matrix multiplication, to give you an understanding of what is the larger process instead of just knowing like a formula to achieve it. So let's look at the two matrices. 2, 1, 3, 4. And let's try to multiply that by 4, 3, 4, 3, 2, 1. Okay. Can these matrices multiply by each other? The answer is no, they can't. And how we find that out is we look at the dimensions of matrices. And this tells us some important information when we look at the dimensions of matrices. So this matrix, we're going to call this A and we're going to call this B. A has the dimensions of 2 rows and 2 columns. B has the dimensions of 3 rows and 2 columns. If we want to see if we can multiply matrices, we like to put the first one, because this is part of the reason why order matters. We put the first set of dimensions and then the second set of dimensions. If these are the same number, we can multiply these two matrices. If the columns of A, the columns of A are the same as the rows of B, we can multiply these matrices. Now, let's actually put that into practice. So instead, let's look at this, a matrix as such. We'll use B again, and then we'll multiply it by C. We'll do it like this. Make it simple. Can these matrices multiply each other? So matrix B and C can be multiplied by C. Well, let's look at the dimensions of B. So we have 3 rows and 2 columns. And then for C, we have 2 rows and 3 columns. Okay, so we can multiply them because these numbers are equal. Now, then what we find is, okay, what are these outer numbers? These outer numbers describe what is the end result, what is the end result dimensions of our matrices, of our matrix, that we get from multiplying B and C. So we actually need to make a 3 by 3 matrix for this multiplication. So that's because we have 3 on the outside and 3 on the outside there. And this is rows and this is columns. So let's look at how we actually multiply these, what we do. What we do is we look, okay, we want to find what is we know that this is 3 by 3. We want to find what is in the first row and the first column. How we find that is we multiply the first row of B by the first column of C. So we do 4 times 3. So that's this 4 times this 3 plus 3 times 3. That's this 3 times this 3. So this multiplied by that in order. And that's why we have to, because of how this multiplication works, that's why we have to have these dimensions working in a specific way, because we want there to be 2 here to multiply by 2 of those. So we want the rows and the columns, the rows of number 1 to match the columns of number 2. So now let's look at, if we want, we're probably going to need a little bit more, probably going to need a little bit more space. Let's look at the column 2, row 1. So to do this, we multiply row 1, column 2. We multiply the first row by the second column. So that's 4 times 2 plus 3 times 2. That's multiplying this again by that this time. Now we want to get the row 1, column 3, so that's over here. We want to do row 1 times column 3, so that's 4 times 1 plus 3 times 1. And that's our first row. Now we want to get row 2, so we do row 2 times column 1 to get the point at row 2, column 1. So that's 4 times 3 again, plus 3 times 3 again, because this is the same. Now we want to get row 2, column 2. So we multiply row 2 of B by column 2 of A. So that's 4 times 2 plus 3 times 2. Now this will be the same as well because we have the same first two rows. Now we want to do row 3, column 1. So we have row 3 of B times column 1 of C. So that's 2 times 3 plus 2 times 2. And then we move forward as such. So we do 2 times 2 plus 1 times 2. And then we do, I made a mistake here, 2 times 3 plus 1 times 3. Sorry. 2 times 2 plus 1 times 2. And then 2 times 1 plus 1 times 1. And this is our result. We would go through and we would actually figure out what is the result of each of these. And then we have our 3 by 3 matrix result. So that's our general process. And you can follow this process for any size of matrix. You are just looking, if you multiply it, you're looking, okay, if we multiplied A times B, you find out what the dimensions are, and then you say, okay, column 1, row 1, column 1, we multiply row 1 of A by column 1 of B. Row 1, column 2, row 1 of A by column 2 of B, etc. So now let's look at the identity matrix. First, I just want to define, if people don't know what an identity anything is. So we have an operation. Let's say we have an operation A squiggly line with an identity. The result will be an A. So a squiggly line could be a plus, could be multiplication, anything. But that means the identity is different in each of those operations. So think about 4 times 1 equals 4, and 5 times 1 equals 4. No matter what equals 5, sorry. No matter what you multiply by 1, it's the same number. Therefore, it's the identity value in multiplication. Now, if we do 4 plus 0 equals 4, 5 plus 0 equals 5. Therefore, for addition, 0 is the identity. And when we do the inverse of a number in terms of a certain operation, that means we would consider what creates the identity when you do that operation on a number. So the inverse of 4 in multiplication is multiplied by 1 over 4, because that creates the identity. It does the inverse. So 5 times 1 over 5, that's the inverse of 5. In multiplication, it creates 1. 4 minus 4, it's the inverse in addition, creates 0. 5 minus 5 creates 0. So that's what the inverse would be in terms of if you're looking at identities, theories about identities. Now, an identity matrix is the same idea. You have a matrix, you multiply it by the identity, it equals the same thing. You multiply a matrix by the inverse of that matrix, it creates the identity. So an identity matrix looks like this. And there's multiple different levels, because remember, you can only multiply A by B, and this time let's do A by I, if this is true. If A's columns is the same amount as I's rows. So if A has 2 columns, you can multiply it by this. If A has 3 columns, you can multiply it by this one here, which we'll call identity 3, and this one we can call identity 2. So we can do that to sort of work with the inverse here. The inverse is basically, the rule of the inverse is you can multiply the inverse by A, and then it will equal 1. And you can multiply A by the inverse, and it will equal, not 1, sorry, and it will equal I. It will equal the identity, because it's the inverse, and that's what the inverse means. Now, the inverse we can actually find from A with this formula here. We have 1, and then down here is what we call the determinant of A. And then we have this sort of complicated factor here, which is we can find sort of differently, and there's extremely heightening levels of complication in terms of actually finding this value here based on how complicated the actual matrix is. If it's 3 by 3, it's very difficult to actually find. So other than your graphics calculator, which you'll probably cover how to work with matrices with that in class, other than with your graphics calculator, you won't actually work with the inverse of a 3 by 3 matrix. Doing that by hand is well, not that you won't work with it, but that you won't actually have to find it by hand, because it's absurdly difficult, I guess. Now, the determinant of A, there are systems of finding that, because it's different depending on, obviously, the size of the matrix. There's some very specific systems of finding that I could recommend you looking up, like how to do it with a 3 by 3 matrix, or how to do it with any size of matrix, because it's sort of useful. It's interesting. But for now, we will just follow this formula that we can always use for a 2 by 2 matrix. So we know that the determinant is equal to this. When the matrix is equal to, doesn't write it down, but when this is assuming the matrix is A, B, C, D, like this. Now, we use the determinant, and then over here, for 2 by 2 matrices, this factor here, we can just say is, we flip basically A and D, we flip the horizontal, we flip this diagonal, and then we flip the signs of that diagonal. So D and A swap, and then C and B, they have flipped signs. And then we multiply that by AD minus BC. And that's, if you can remember that, it's useful. But also, if you can look up how to find the general way to find a determinant, it still does help understanding a little bit. Remembering this, though, is completely fine. Find the inverse. So first I'm going to do the determinant. So that is 3, we have 3, 4, 9, 8. The determinant will be 3 times 8 minus 4 times 9. And that's all over, for this formula here, we have to put 1 over that determinant. And then this factor over here, we flip the 3 and the 8, and we put -9 and -4 here. So that is 120 over 24 minus 28, 8 minus 4 minus 9, 3. This is my mistake here. This is 36. Now, that is we can simplify it a little bit, but this is our inverse matrix. You could optionally, if it seems convenient, actually move this scalar product into being a factor of each of these, but for now we don't actually need to do that. What is the property of A times the answer of part A? Well, the answer is I, because we know that because it's A times the inverse of A, we know that it's equal to I. So there's our answer immediately. So we can use this understanding to model a solution for simultaneous equations. And now this is very, very useful in calculator, and there's often a 1-mark question on the exam for a very annoying simultaneous equation that you can just immediately do with matrices, and it might have fractions and stuff in it to a point where it's awful to actually solve by hand. And basically, if we can plot a simultaneous equation as shown here. So x, y, z, if we put them in the right order, you can put that in there, and then you can put all these here, because you can expand this out. If you expand this out, you will be able to see that it actually results in the same thing here if you expand all these matrices out. You don't need to do that, though, because we can just look that we can just know sort of that it works and then apply it during the exam. So you put x, y, z in this vertical matrix, and then a, b, c, a, b, c, a, b, c, whatever. Now, we have this basic structure that is best to memorize, and then we can actually utilize matrix algebra to do it, because we want to find what x, y, and z are. So if we put x, y, and z here, now, if this is multiplied by a, we'll call this a, and this equals b. Now, if we want to get x, y, and z on their own to find what they are, we can multiply both sides, and remember that order matters. You can't do it like this. That's wrong. If you put the inverse of a out the front, you have to put it out the front again. So we can do the inverse of a by both of these, put the inverse of a out the front of both of these sides, and you have to put it out the front, because if you put it out the back, then you're not actually getting the identity, because you're multiplying the inverse of a by x, y, z, which is incorrect. So basically, if we have a, x, y, z, which you can plot in your calculator, then we can multiply the front by the inverse on both sides. And that immediately cancels everything on this side, because you know that's the identity. So then it becomes identity multiplied by x, y, z equals the inverse of a times b, which you can just solve on your calculator. And this cancels out itself, because the identity multiplied by anything that it can be multiplied by, it's just the same as that thing. So then you have your answer when you figure this out on calculator, which is very fast and quick. So let's actually work with inverse matrices and the identity matrix. So let a equals this and b equals that. Evaluate a times b and hence determine the inverse of a. So looking at this, I can figure out if I multiply a times b, it's probably going to be equal to something, let's say the inverse, that tells us that b is actually the inverse. So let's say the identity matrix, sorry, that tells us that b is actually going to be the inverse of a, which is what I'm suspecting. We'll find that out. So let's multiply these together. Now let's look at their dimensions first, like we looked at before. It's 3 times 3, and then 3 times 3. They can be multiplied because these inner dimensions match, and these outer dimensions describe to us that we're going to be having a 3 by 3 matrix. Now I'm going to put this border all the way over here, because we're probably going to have to add a lot of little pieces. So let's look at row 1, column 1. What is the value of row 1, column 1? So we get row 1 of A and multiply by column 1 of B. So that's 5 times 2 minus 2 times 1 minus 4 times minus 1. Now we're probably going to need even more space than this. We'll leave it open. So then column 2, row 1. So we do the row 1 of A times column 2 of B. So 5 times 2, negative 2 times 1, negative 4 times 2. Now over here we're doing row 1, column 3. So row 1 times column 3. And we can continue to go down. Row 2, column 1. So that's minus 1 times 2 plus 6 times 1 plus 4 times minus 1. Row 2, column 2. So that's minus 1 times 2 plus 6 times 1 plus 4 times 2. Now, we can probably put the borders here. We have row 2, column 3. So that's minus 1 times 4 minus or plus 6 times minus 4 and plus 4 times 7. And we can finally finish off with row 3. So we have row 3, column 1, 1 times 2 plus minus 2 times 1 plus, we can ignore the zeros because they're obviously going to just cancel out everything. So we have 1 times 2 plus negative 2 times 2. And then finally down here we have 1 times 4 minus 2 times minus 4. Now, we're going to try to figure out what this is, and we can assume it's probably going to end up something like an identity matrix, because we are expecting that A times B tells us something about an inverse. So B might have some relation to an inverse. 5 times 2 is 10, minus 2, plus 4, 12. Then 10 minus 2 minus 8 is 0. We have 20 plus 8 minus 28 is 0. So I'm starting to see a pattern here. We have minus 2 plus 6 minus 4, 0. We have minus 2 plus 6 plus 8, that's 12. And then I might be able to assume that the rest of this equation, I'll just check on these last two ones. So that's 2 minus 4, but I'm probably made a mistake. This is a good way to check your mistakes if you think you know what the answer is. So we can look down here. This is row 3, column 2. So this should be 1 times 2, and then minus 2 times 1 is actually the answer. So yep, this culminates in 0 as well. And then we have 4 times 8, 4 plus 8, sorry. So that's 12. So that means that A times B was equal to 12 times the identity. Now this means that I can assume we can divide, I can assume A, 1 over 12A times B is equal to the identity, which means I can just comfortably shift, since again, scalar multiplication is commutative, we can shift this scalar, this magnitude around. So I'm actually allowed to do A times 1 over 12 B equals I. So that means I think B is equal to, or I think that my inverse is equal to 1 over 12b. And that would be 1 over 12 in front of all of this stuff here. So hence solve the following system of simultaneous equations. So I can say, okay, B is, my inverse of A is equal to 224 1 minus 4 minus 1 2 7, and that's all. I can't forget to put the 1 over 12 out the front there. So we want to solve the following simultaneous equations. So we can put A down first. So this is what A is. Minus 2, minus 4, minus 1, 6, 4, 1, minus 2, 0. Okay. So now that's the same as what we have here. We can multiply that by x, y, and z. And then we know that this equals to 24, 12, and 0. So now, again, following this system that we're using here, following the system of finding simultaneous equations that we were using over here, that was described here, we can consider A times x, y, z is equal to 24, 12, 0. We can consider multiplying everything by this. So then we get x, y, z on its own. So that would be x, y, z is equal to the inverse, is equal to 1 over 12, 2, 2, 4, 1, 1, minus 4, minus 1, 2, 7, all multiplied by what we had on this side. So that's 24, 12, 0. So comfortably we can look at this and we can see that this is 2 and this is 1. So we would do sort of a simple matrix multiplication to finish this off just like we sort of did over here, which this was a much more complicated one than we'd have to do here. We may as well just actually quickly do it. So we have, it's actually probably going to look sort of more like this, but we will, let's consider the dimensions first, as usual. 3 times 3, and then we have 1 times 3. So, sorry, 3 times 1. 3 times 1. So that means our final dimensions are going to be 3 rows, 1 column, which is good for us. That's what we want. And now we can find, okay, so what's in position row 1, column 1? We have 2 times 2 plus 2 times 1, and then we could ignore the 0. So then down here we have 1 times 2 plus 1 times 1. Down here we have minus 1 times, to minus 1 times 2, and 2 times 1. This is equal to 6, 3, and minus and 0. So that is the answer that we get from our simultaneous equations. We know that x, y, z is equal to 6, 3, 0. So x is equal to 6, y is equal to 3, and z is equal to 0. Now, there could be a mistake, but no, it looks like that's correct. It's very easy to make a mistake here. Luckily, there's lots of carry-through marks for questions like that in exams. So this is our final topic. We're going to look at dominance matrices. Now, these aren't very complicated. These are pretty simple. Basically, it's just a way of considering and ranking round-robin competitions. So when a group of people compete against each other and each of them competes against everyone else, and then we want to accumulate in some way, aggregate in some way, the wins that they all had, we can, in a very simple sense, just put them in a matrix. We can say, okay, we have A, B, C, D. We have A, B, C, D. Okay, A defeats C and D, so we put a 1 and a 1 there. B defeats A, so we put a 1 here. So this is who's defeated, and this is who defeats. C defeats B and D, so we have 1, 1 there. And D defeats B, so we have a 1 there. And everywhere else will just be a 0. So there you go. Everything else will be a 0. So, yep, everything else will be a 0. So that's probably about right. Yep. So basically what this is saying is if you just read one of these, you're saying, okay, A on the left side defeated C and D. So this represents who's defeated, and this is who defeats. Now, this isn't that useful. You could look at this and say, like, okay, so that person has 2 points, that is 1, that is 2, that is 1, but that doesn't give us actually much value. What we can do instead is we can do multiple orders of dominance matrices, is what we call them. So when we multiply a dominance, when we square a dominance matrix, it does something very interesting. So if let's say A defeated B, C, and E, then if D defeated B, it's less valuable than if F defeated A, because A is more valuable to defeat in this ranking system that we're building, because A was able to defeat multiple other people. When we square a matrix, it's basically taking into consideration if you were able to defeat someone that was able to defeat more people, because the way in which if you actually did the multiplication by hand, you'd see that it would culminate in basically you getting more points if someone you defeated, because your points get multiplied by their points. You would get more points if you defeated someone who defeated more people. And this allows us to sort of have a bit of a ranking system which takes into consideration values of someone you defeated. So this is a simple scenario of squaring this dominance matrix. Now, A has more points now because A was able to defeat C, who defeated more people than everyone else, other than A. So A is winning now because the difference between A and everyone else is A got 2 points, and it was also able to defeat someone who was especially valuable. And that's basically what dominance matrices are. So when you are making a ranking with dominance matrices, you get M, which is just the simple like system we described before. That means A defeated C once and defeated D once, B defeated A once. And then you're able to add different powers because you can keep going further and it will keep adding more. The problem is as you go up, it'll get exponentially more valuable. So you tend to add arbitrary coefficients to the front of the higher power matrices, but it is completely arbitrary. When it comes down to it, when you're using dominance matrices and you're using powers of dominance matrices, you are creating an arbitrary system of evaluating matches, of evaluating round-robin matches. And this is useful in applications of, for example, basically, usually the biggest example that I see people try to apply it to is being able to predict who will win another time based on previous wins. So you're sort of giving a ranking to how good you think someone is, therefore how likely they are to win. And that's the system of dominance matrices. So I think that mostly wraps us up in terms of content. We covered induction, so basically a way to solve things with a sort of recursive method that's able to prove for a well-ordered set that there's a consistent rule. Then we covered vectors, covering a lot of what we already covered before, and then going over some proof stuff. And then matrices, so just some operations we can do in matrices, and then the application of these dominance matrices, which are pretty simple to be honest. If you like look at them at a basic level, partly because they don't really need you to solve anything per se. Like there's not any truth towards the value they create. They're a little bit arbitrary, but they can be used to maybe like predict things. So in general, how would I recommend you move forward with sort of an understanding if you want to get a bit more of an understanding before like school starts? I would go through the syllabus. I would sort of write down things from the syllabus and write down the types of questions you think the syllabus needs you to know, because even if you do that at the start of the term, as you move through the term, you will be able to concentrate on the right things in class, basically, because we're not all going to concentrate on everything in a class. But if you know what you need to know, if you know the kinds of stuff you need to know, you will know what to look for, and you might connect more with some of the more important information. Now, as we start to get the basics down, I'd recommend try to do quite challenging questions. If you keep doing the basic questions, you'll get more comfortable with them. It's not that there's no value there. It's just that it's specialist, there are hard questions. If you want to do very well, you're going to have to get used to these very complicated questions. Now, if you run out of questions, you can just find them. Like you can find so many questions for any of these topics on the internet. And there's multiple textbooks, and we have resources at ATAR Notes. So there's not really an excuse to say like you've run out of questions. You can always find more if you do want to do more study. So these are just some points. It's a little bit cut off down the bottom there, unfortunately. But these are just some points about what you can do as little tips for these topics we've been over. So it's probably valuable just taking a quick look at that. If you could pause this after it's complete or take a screenshot. Now, with induction, as I said, it's largely about a process that you'll get good at when you just keep doing it. The process will become intuitive. You do just have to practice it a lot. And it's not fun to practice because you're rewriting the statements over and over. But it is, and there's way more complicated induction questions than what we went over. But if you get the process, even if you're not going to get it in an exam, you can show that you know the process and you will get 50%. Now, with that, I would recommend do just go through the main textbook ones at the minimum, but you can look up any of those on the internet. So in terms of improving on your mistakes, lots of high achieving students will just make lots of silly mistakes, and that's my experience as well. I often lose lots of marks during exams from just little errors. To overcome that, my solution personally was that I would write down whenever I made these mistakes, and I would go back, and before doing any practice exams or exams, I would look at these mistakes, and then I'd finish the exam, make sure I look to see if I made the mistakes, such as not putting a unit down, or just copying down a question incorrectly, like copying down a statement incorrectly, which will obviously destroy your whole method of solving a question. Now, I think doing that, following that process, and also writing notes, even if you're looking at answers, writing notes about how they solved questions, writing those notes down is really valuable. So write notes on your mistakes and write notes about how questions are solved, even if you're just looking at the answer because you can't figure it out yourself. Do write it down by hand and do review it quite consistently if it's a question that you have trouble with, because you will eventually just get it if you keep looking at how it's proved. And if you really can't understand how it's proved, it's obviously good to go to your teacher, or try to look it up online perhaps as well. So in terms of during an exam, and that means, like, really, I personally believe anything that you'd want to do during an exam, it's probably good to do it while you're just practicing as well, while you're just working in your workbook, because obviously that there's value in building those habits. So again, these are my sorts of notes. Check you've written every formula correctly. I often write down a formula incorrectly, or even write down the question, the values of the question incorrectly. Make sure that all your arithmetic is good when you check back over. Like, try to give yourself just that bit of time to check back over these questions and make sure your arithmetic is good. In Tech Active, and you should just plug everything in the calculator again. Like, people will make mistakes while plugging everything into a calculator. There's a lot of stuff going on. So do recalculate if you have any time to do so. Now, writing down your errors is useful because you can also find out where you have faults that you can concentrate on and be conscious of during exams. So, doing specialist is boring, to be plain about it. But if you want to do well, whether you want to build your knowledge up to succeed in university, to succeed in mathematics, or just to get a good ATAR, because we know specialist is very good for that. You will just have to suck it up and be bored while you're doing a lot of questions, probably. Most people don't love maths, but how you're going to do well and how you're going to really maximize your ATAR is you're going to do the work. So don't just try to build some sort of habit that you're used to doing the laborious work that you need to do. And so that's it. If you have any questions, just send them into chat, and I or someone else, probably me though, should be there to answer any of your questions, including any personal ones about like university or your coming experience in the final grade of high school. Okay.